In this video, we'll take a look at how to guess what the sign of delta S will be for a particular process. And we're going to look at several different scenarios. The first one we'll look at is the state of matter associated with our particular system. We know that solids, liquids, and gases would be the three states of matter that we work with here in chemistry. No Bose-Einstein condensates for you. We'll just look at these. If we want to think about entropy in this, we want to think about how they can move. With solids, all they can do is vibrate in place. Solids only vibrate. Liquids can vibrate, gases can vibrate too. But solids can't move in any other way. Solids can only vibrate. They're very organized, and they're rigid, and they don't really move other than vibration. With liquids, we also add rotation. Liquids can rotate around. Water molecules can spin around because they are not locked in position anymore. And gases, of course, can do that too. Rotation. And then finally, we have the ability of liquids to move past each other, and that's called translational motion, where they can just move past each other. And liquids do that on a small scale. They can move a little bit. But gases have major translation, right, in terms of motion. Translation, again, is motion like to the left and right. Rotation is spinning around. Vibration is, just vibing in place, right? So we see here that in terms of motion types, solids have very limited ability to move. And so we generally have low entropy for a solid. We have medium entropy for liquids because they can rotate and move past each other. But gases are where we see a very high entropy because gases have the ability to zip around all over the place. And they're able to move in all the different ways, and they have a ton of microstates associated with them. For water molecules, it's like, yeah, I'm over here, you're over there. We can kind of move around each other a few states. But for gases, I can be here, 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 here. So we have a lot more options available to us in the gas state. So generally speaking, gases have the highest entropy of our states of matter. And so we can predict, I guess we don't really need a delta for this because these are single states, but delta S for the processes becoming a gas will always be, will have a positive delta S because your final state would be a gas. Whether that's whether you're a solid or liquid becoming a gas, you're going from high entropy as your final state, medium or low entropy. High minus medium or low will be a positive number. So you'll always be entropically favorable to become a gas. Solid becoming liquid is also going to be entropically favorable, right? Because liquids have more freedom, more ability to be disorderly. They have medium entropy. Medium entropy minus low entropy would be some positive number. And of course, becoming a solid or a gas becoming a liquid will have the opposite case. You'll have a negative delta S. You're becoming more organized. You're taking away the freedom of motion. And so for both of those, the delta S will be less than 0. All right, so that'll be negative entropy where we're getting more orderly. More disorder for these processes, more order. So that's one way we can predict what's going to happen in terms of our qualitative approach to is S increasing or decreasing throughout this process. Another way we can look at this is some gas to more gas. That would also be an increase in entropy. For example, the opposite of our favorite equation, we're going from 2 moles of gas to 4 moles of gas, right? So, because we're producing more gases, we'll see that delta S will increase as this reaction proceeds in this direction. So we're becoming more entropically favorable, right? Delta S increasing is a good thing. That's what the universe wants. So energetically speaking, that's favorable. Of course, there are other things we can predict as well. If we were to take a look at, for example, the entropy change associated with solids and liquids, those become a little bit less obvious to us. Somewhere it's clearly, we're going from all, one liquid, one solid to one liquid and one solid. What do? Not really obvious to us, right? But in other senses of reactions, we can take a look at making more complex molecules. For example, if we take, let's say we're going to take C6H12 and burn it. We're going to make CO2 and water. And let's see if we can balance this. Oh, thank goodness, it's an even number. 6 plus 12 is 18, so we need 9 oxygens. Here we're going from, let's say it's a liquid, we're going from 9 moles of gas in a liquid to 12 moles of gas. We might be predicting to say, yes, this is going to be more entropically favorable. But now we're dealing with a particularly complex molecule on the left side. We see that for complex molecules, entropy also increases because those complex molecules have more tendency to be able to do different things. Like they can arrange themselves in particular ways. So for polymers, for example, they typically have very high entropy because they're extremely large molecules. They can twist and turn and do all sorts of crazy things. And so this might be hard to say. This might be difficult to predict because entropy typically increases with molecular complexity. And also with molar mass, because molar mass, as we know, means more electrons. More electrons means more ways of distributing those electrons. We saw the London dispersion forces as electrons decide to zip all over the place. Those are microstates. So with molecule complexity, and it also increases with molar mass. So it becomes a little bit difficult to predict when we're going from a particularly complex molecule to simpler molecules. Even if there are more gases, it may be difficult for us to predict qualitatively. So with things that are obvious, like phase changes, something boiling becoming a gas, absolutely delta S is positive. No second thoughts required. When we are dealing with maybe the same moles of gas on one side as the other, it may be tough. We have to look at the complexity of the molecules, and that's not something we can do very easily. Right? We can make predictions, but mathematically we may not get the right answer. And so, therefore, it'd be nice if we did have a mathematical way that we could actually calculate delta S based on a reaction. And lo and behold, we can. We'll see that in the next video.